So welcome to the fourth lesson of the Automating GIS Processes course. We're now halfway through the course, 3 lessons done, 3 to go. And today we will continue with kind of spatial overlay analysis first, in a way continuing from what we did last week. So last week, after geocoding, we learned how to ask questions about spatial relationships. Is a point within polygon, do 2 objects intersect, and then join attributes based on that information. Today we will learn how to then actually modify geometries based on this kind of spatial relationships, and then continuing to some other types of geometric operations. For example, we will learn how to dissolve data. So if we have some smaller spatial units, we can then combine those into larger spatial units using this dissolve function that then aggregates the data. So that will be the first part. And then the second part, we will move on to reclassifying data. We will use this travel time matrix dataset that you have already been using in the exercises, and then see how we can create classifications based on the travel times, both in the data as labels in a new column, and then on the fly when we are visualizing the data on thematic maps. And that then provides the basis for next week's lesson, which is about data visualization. So next week we'll focus fully on plotting maps using Python. All right, be ready to start. So this week's lesson is quite relaxed. There's not too much content related to last week's lesson, which was quite full of new things, but I did add one new section, a bit of a more applied example related to geometric operations and the COVID situation. So let's see if we have time to go through that tutorial as well. Might be a nice opportunity to refresh some of our pandas skills and then deepen our GeoPandas skills as well. But overall, during this lesson, you will learn how to do overlay analysis, modify existing geometries based on spatial relationships, aggregate geometries using this dissolve operation, simplify geometries, so manipulate geometries in different ways. And then the second topic is related to these data classifications. All right, and maybe still one word for those who are not from Finnish University Institutes. You should be able to launch Binder from the website from here, which will then, it takes a bit of time to launch, but then you will get this Jupyter Lab instance with the tools available. So also for the Helsinki University students, if everything is down at CSC, you can go to one of these lesson pages and then launch Binder and then work from there. But over there, I think we don't have the Git plugin installed. So then you will need to either download your files manually or then use Git from the command line to save your files to GitHub. All right, excellent. So let's go. Starting from geometric operations over at CSC notebooks, you can find the files under AutoGIS notebooks lesson 4. I hope you can see those files in there. We have fixed the setup script a bit so that there shouldn't be these issues of not having the files. But in case there are some issues, please let me know so we can always improve the behind the scenes stuff. Okay, and so we start from this geometric operations notebook, and related to that there is some input data in the data folder. And I think we are also then downloading some data. So let's get to it. As I mentioned, we continue with the similar topic from last week. So looking at these spatial relationships, intersection, and then in addition, these kind of from set logic, these different logical operations such as union, so the combination of two areas or sets difference in different ways. But in this lesson, we will mostly be using this intersection operation to create new geometries based on overlapping layers. And as we are talking about spatial overlays, then of course, understanding coordinate reference systems and verifying that the data is in a unified coordinate reference system is the starting point for such overlay analysis. So we need some data to work with. Actually, let's see what we have in here. Could somebody let me know if you actually have these files in there? I think you don't. Do you have a lesson for data folder? Might actually be that you don't have it. Yes, you have. And you have these files in there. Yes. Okay, excellent. Let's see if we actually even need to download the data folder. I think Helsinki borders, travel times. So yeah, okay, let's continue. And in case we're lacking some data, then we can download them from this zipped file and run that. So we can indeed start by importing the data. Now, if we indeed have them in there in our instance readily, that's nice. So we will take 2 layers as the starting point, Helsinki borders, and then 1 data file from this travel time matrix dataset that has then already readily been joined with the spatial grid file. So this is both our shape files that we have in the data folder, and we can then start by reading in the data using the skills we already have. So let's create 2 variables, grid and Hel or Helsinki. So the grid file is then this travel time matrix grid. So we do using GeoPandas, short for GPD, gpd.read file grid fp. And as we learned 2 weeks ago, Esri shapefile is the default file format when reading in files with GeoPandas, so we don't need to pass this driver parameter. Same thing for Hel, GPD read file, and then this border FP. So we have 2 polygon files. We read them in from these files in the data folder. So this is again a relative file path, as the data folder is located in the same root folder as our working directory. So then we can refer directly to the folder name and file name, which makes it then flexible. This syntax will work on different computers if you just have the project files somewhere. Okay. When I proceed, if I'm going too fast or skipped something important, please let me know. I have the chat window so that I can see it. Okay, so maybe I'll still add 1 grid cell, or sorry, code cell in here. Always good idea to do this layer.head after importing the file. So we have some columns, we'll check those later. And then the geometry column, of course, as it's a geodata frame, but the data looks correct. And then hel.head. Okay, so we can see that this grid, there's multiple grid polygons, and then Hel is just 1 polygon for the Helsinki borders. So those layers we want to overlay. As it's spatial data, let's do kind of a quick exploratory plot out of these layers. And as we have learned, there's different ways of plotting, but using GeoPandas, we can plot the data kind of quickly without importing matplotlib. So we can do grid.plot, just like that, to start with. And then, well, as we will be plotting them on top of each other and the default color is always blue, so let's change the color. So face color changes the kind of color of the interior in the polygon. Put something lighter, as we want that into the background. And now if we want to just quickly plot this Helsinki polygon into the same figure, assuming they are in the same coordinate reference system, and based on these coordinate values, it looks like things will be somehow in the same coordinate space. We can actually do a little trick like this, so that we store this figure object or plot object into a variable. So it plots it, but at the same time we have this variable that is actually the plot. And then when we plot Helsinki, so hel.plot, there is this AX parameter to indicate to which subplot object we want to plot it. So we can say AX is the previous figure object. And then we could plot it as transparent, so no color for the kind of insides of the polygon, and then edge color, we can put some color. I think it would be anyway by default blue. So this is not yet kind of, we are visualizing, yes, but it's a tool for exploring our data and verifying that things are as expected. So here you can see, those who are familiar with the Helsinki region, we have the Helsinki municipality. The polygon extends to the sea towards Estonia. And then the city center is over here. And then this travel time matrix data grid, which has 13,000 grid squares and a bit more, extends over the 4 municipalities. So there's Vantaa, Espoo, Kauniainen in addition. And to exemplify a simple overlay analysis, we want to cut the grid using this Helsinki polygon, just to focus our analysis on Helsinki. We could also buffer Helsinki and have a buffer around and then cut it with that, or any other polygon borders. Okay. So already based on these coordinate values in here, and based on the plotting, we could be quite confident that the coordinate reference system is the same in these 2 layers, but we want to verify it using Python, just to be super sure before continuing with the overlay analysis. So I could give you a few moments to check using Python if the CRS of this grid and Helsinki are the same. I forgot to put this check your understanding, but try to do it yourself, and I'll show in just in a couple of moments how to do it. So check if the CRS of these 2 layers, grid and hel, are identical. Okay, it's not a long piece of code, so I will now start showing how it's done. So if we just start by checking the CRS of 1 layer, we can write hel.crs. and seems that hell is in the projection EPSG 3067. This prints the kind of PyPro CRS object definition. You have all these details in here. If you want just a quick info, you can print this object, and by default it prints the EPSG code. We could then of course do the same for grid. Excellent, it's the same, but then to really ensure that the definition matches, like there's nothing different, we can then of course do this hell.crs grid.crs Boolean comparison. So that is true, we have a matching coordinate reference system. And if you would build this check into your bigger analysis workflow, you could have an if-else structure. If false, then reproject one to the other, or then just an assertion that then throws an error. CRS do not match, whatever. So in case these would be different, then your code would stop here and give an error message. So that's, even if you assume or kind of know that they are the same, always good to build in a check that really checks if the coordinate reference systems match before proceeding with overlay analysis. And then indeed the way to reproject would be then to use the toCRS function that we covered, was it 2 weeks ago? So you can find more details under lesson 2. So now we are ready to proceed, and the goal is to create a new layer that has the geometries from the grid polygons, so that we only have the intersecting part with the Helsinki layer. So in GeoPandas, there is a function called overlay. Maybe we'll quickly see the documentation. GeoPandas overlay. So again, you can check the original documentation. This is not so lengthy, but basically we have 2 data frames, then the rule based on which the spatial overlay is done. Do we want the intersection union or some of these different options? And then there's different settings if we are, for example, doing an overlay with mixed geometries. If we then want to restrict the output to the geometry type of the first layer. Was this the one? Yep. So let's call the output intersection GPD overlay, and here the order matters. So we want the output to have geometries of, or the kind of each row of the data would be a grid square, but so that we only have those parts that intersect with Helsinki. So we would put grid first, intersecting with Helsinki, and then this how parameter is intersect. And then I probably intersection. It takes a moment, but not too long with this small data. So now we have something in this intersection, and let's see what we have. I'll maybe do like this. So indeed, this now looks like the grid data. So we have many rows of data, but how does it look like if we plot it to the map? So now, if you look closely compared to here, so the original shape of the grid file covered the whole region. Now we have cut it so that it only covers Helsinki region. And if you would look really closely, this is maybe not the best example, but we have actually also modified, so the edge, we have kind of cut those grid squares that are at the border. So in some cases, you might then want to just to do a spatial join in a way that you select all the grid squares that intersect. In this case, we are kind of cutting out, if, for example, visualizing a map or something, you might then want to actually cut the geometries that intersect the other geodata frame. Another example would be sometimes you might get finished municipality polygons so that they extend over to the sea area. So Finland looks kind of like too round compared to the kind of coastline shape. So then you could cut the municipality or overlay the municipality polygons with Finland in order to then get these nice municipality polygons that go along the coastlines. Okay, we can then continue checking what we have. Intersection head. So indeed, the attributes are now from the grid dataset. We have not joined any attributes from the other file, if I'm not mistaken. Let's double check. So actually, sorry, I take that back. So we have also joined then these attributes, so kind of identified that all of these grid squares were in this Helsinki polygon. So we get a spatial attribute join at the same time. Yep, so attributes from the both input layers based on the intersection. And let's imagine if we would have had all the municipalities from the region, then we would get these kind of cut grid squares on the border and then labeled according to the intersecting municipality. Yeah, so that's it. Let's save this file. I think it already exists in the data folder, but just to show how to save it for further purposes. So the file name is defined in here readily as it's a bit longish. So we have the data we actually have, we will explore it further later on. So we had this travel time matrix grid with travel times to a specific grid square. So across the whole region from each grid square, travel times to this one particular grid square, which happens to be the railway station in Helsinki. And in the after the break, we will then visualize this data and classify this data. So for that, we save to file, and to have some alternatives, we will save to GeoJSON. So for example, if you want to share a map on GitHub, I think it needs to be in GeoJSON format. So GitHub is also able to render maps in web Mercator projection, and for that the file format needs to be GeoJSON. So we can have this out FP, and now that we want to write some other data for spatial file format than S3 shapefile, we specify driver GeoJSON, which we covered also in the previous. There we go. So latest now you should have in the data folder this zip, this file that was now updated seconds ago. Yep. All right. So as mentioned, with this GeoPandas overlay, you can then do, if you want to union two sets of geometries into one larger layer, you can do that. So if, for example, you happen to have some, what would be a good example now, you have some island polygons that are in separate file for some reason, or whatever data scattered in multiple files, you can read them in, make a union union and create a layer with those geometries. Then that overlap will become one geometry. All right, so there is one green check mark. Maybe I'll erase that. If you have any questions at this point, please be active. But this is quite straightforward. And just to sum up, the difference between this and then the normal spatial join is that we actually modify the geometries, but that I already said. Next, we will move on to aggregating data or dissolving data. The example in this notebook is a bit arbitrary. In the following tutorial, we will have a real case with the kind of health district polygons, but let's walk through this simple example first. So if we look at the attributes we have in here in this travel time matrix data, so these different columns represent travel times using different travel modes, so car, public transport, or walking, different times of the day, so midday and rush hour, M and R, and then this D letter is for distance and T letter is for time. So for example, from this grid square, it's so many meters distance using car. So we have pre-calculated it via network distance, and then it's 41 minutes using car from this source grid square to the railway station. And then the same results for public transport, walking, and so on. So you can see that, for example, from this grid square, it's quite a lot faster to arrive to the city center using your car. So we will use some of these attributes now to further process the geometries in here. And in particular now for this example, we will aggregate the travel time data by car travel time. So car, rush hour, T. So let's do it first and then see what we actually created. So the operation is called dissolved. So let's call it dissolved. And we have this starting point, the intersected data. So the grid square is covering Helsinki. And if we use this GeoPandas dissolve, let's actually check the documentation from here. So it's in a way a grouping operation, so aggregation operation, but here we group, or behind the scenes, GeoPandas groups the geometries and then produces some larger entities. But as a process, it's a bit of the same thing that we have already done with group by for attribute data. So it will unify geometries based on some attributes. And if we then dissolve this grid data by this car travel times, so what it will do, that it will take, if we have, for example, grid squares that are 30 minutes travel time, those will become one unit, or one kind of unified row of data with one geometry object representing them. So it's in a way kind of simplistic classification, but we will later on then learn a bit more smarter way of classifying this data. And how does it then look like? So you can see that the attribute by which we dissolve the data, so in this example, the car travel times, we get that into the index. So -1 in this travel time data represents no data values. So the first one is that. Then the second one represents all those grid squares with 0 distance. So it's probably the destination grid itself. And then in the index, we have all the distinct travel times that are throughout Helsinki to the Helsinki railway station. So let's check a bit further. If we check how many rows we started with. So in Helsinki, there are, oops, need a comma. So some text, comma, some value will print out the number of grid squares in Helsinki is 3,000 and something. And then in this dissolved layer, now that we have combined the values based on travel times or unique travel times, we see that then this dissolved layer has less rows. So there are 51 distinct travel time values across the region to Helsinki, and each of these or the group of grid squares is then represented on one row. Okay. So if we look at the columns, so we have the original columns, but excluding the one that we used for aggregating the data because it is in the index. So then the values in the index are the unique values that we had in the column that we dissolved by. And then the name of the index is the name of the column. Okay. So we can process this even further if we want to reduce the amount of data that we have. So now that we have the travel times in the index, we can use that as the basis of kind of minimizing our data. So if we would want to select those geometries, so those rows that are within 15 minutes away or exactly 15 minutes away, we can select index 15. And then this polygon would represent all of those grid squares in the data. And that indeed is one pandas series. This is maybe not so useful if you don't have time to type it in, not to worry. But now we have picked one row of data in this geodata frame, and that is a pandas series. And then I again copy paste this one. So, well, it was actually already in there. So we could then further, for example, save these into file or whatever we want to do with those. But let's visualize them. That's the more interesting part. So if we visualize to the background this dissolved layer, plot. Let's put it as gray again. So here we can't, as we are not using any color scheme, we can't actually see the classes. We could, of course, then visualize it using a color scheme that we will learn later today. But for this example, oops, I actually, sorry for jumping around. We need to save this. As a selection. I think I lost it at some point. Wait. We have a selection Yes, so we want to select, or we have kind of this selection, but as mentioned, it is a pandas series. So this is a common thing when modifying geometries, taking some attributes, maybe selecting some rows of data. So you might at some point lose kind of the spatiality of the layer. So in that case, now that we have a pandas series with information of the polygon, but the data type is pandas series, we can take that and convert it back to something that then we can plot on the map in here. That was the point. So if we do GPD geodata frame, so the geodata frame constructor, and then pass this pandas series, and I think we need to pass it in a list. So if we would have a list of pandas series, then each of those would become one row of data. And then we can on the fly define the CRS from the original data. So now we should have kind of a one-liner that is actually a GeoPandas geodata frame, so that we can then again plot it in here. Like this. And to make it more visible, it's always a good idea to have some red on a map. Yeah, so this was maybe a bit difficult to follow. Sorry about that, but the point here was that we took one value in this layer, dissolved layer, and then created a separate layer to put on top of the original data. And now, as we had dissolved the data, then all of these partials in here are part of one multi-polygon object. But in the next tutorial, we will have another example of this dissolving operation using municipalities and then combining those into healthcare districts based on the attributes that might be then a bit more easy to follow. Great.
Hello, Boko.
Yeah.
There is an interesting question in the chat that it's saying about selection with a 15. Maybe you can answer it.
Yes,
I think it's important.
Didn't we just select the 19-minute cells? Let's see. So you mean in here? In this one, I think you mean. So now that I'm selecting, if I'm selecting from the dissolved, very good question. So if I have the dissolved data, so there the index label, so now we are operating on the index label, not this kind of numerical index from 0, 1, 2, 3, but the index label is -1, 0, 7, 8, and these are minutes. So if I select, it went a bit fast, but I'm now using this, yes, that's actually, no, let's see, name 20, aha, you are correct. Yep. Think, what if we do like this? Yes, so yeah, thank you. So it should be, if I'm using, that is very correct. Yes, so here we should be using the loc, which takes the index labels, and now like this, I'm selecting the correct one. So that's true. I think, yeah, there might be some path dependency. We have changed this lesson before. There was this IX operator in pandas that worked in a bit different way. So indeed, this iloc operates on the 0, 1, 2, 3, 4, 5, and then loc operates on the axis labels. So now I should be selecting the 15 minutes polygons. Let's see if you agree. And maybe here, even to exemplify, I could do loc -1, which should give me the first row of data, which is in here, right? That matches. And then selecting this 15, which is not visible in there, gives me that row. So let's correct that one. I haven't been paying attention myself. And then there, let's see how that changes, and the map might be more. Yes, so, and the map makes more sense as well. If the Helsinki railway station is here, so then the 15-minute zone is somewhat circular still. So 15 minutes by car from all of these locations. Thanks for paying attention. Yeah, excellent. So good. Students are more awake than I am. And I think we have had this mistake in the lesson materials as well. So I will update that accordingly. Okay, so maybe this was a better lesson about pandas loc and iloc and indices and selections than the actual dissolving. So, and I think I'm also here operating in the wrong code cell. So let's move forward from this notebook. There's still a final part with simplifying geometries. Now I would opt for me showing it from the website so that we can actually still have time to cover this other example with the municipality polygons, which I think it's rather interesting. So in case for mapping purposes or whatever else you need to kind of simplify geometries, that could be the case with coastlines or river polygons like in here. So we have a little example of the Amazon River as a shapefile in the data folder. You can read it in. You will get something like this. You can check the details of the projection as well. And then GeoPandas has this simplify function with some tolerance value that will then simplify a line according to the settings. So then it will kind of reduce nodes and reduce details from the input geometry. So in here, the tolerance is 20 kilometers, as Amazon River is quite long. But then you get a rough idea of the shape, even if simplified.